Okay, so good afternoon. Um, I wanted to do a quick review. The last time we were looking at eigenvalues given a square matrix. um, we said that we can find some scalars, numbers in a field. In our case, it's a real number field, real numbers. And we multiply with a vector and also multiply with a matrix. We find equality. What I'm talking about is AX or AV. Let me just say what I'm talking about. So if I have a square matrix A, and I can find a non-zero vector V, which I multiply with, and I can also find a corresponding lambda scalar or constant number, which I multiply with the same vector V, and I get this equality. If this occurs, then we say lambda is an eigenvalue of our square matrix, and the corresponding eigenvector is V. So I believe we looked at how to find the eigenvalues, lambda. And in case you don't believe so, I can remind you it's not too complicated. You just find what you call a characteristic polynomial, P of lambda, which you just do express, you find the determinant. So characteristic polynomial is the determinant of the matrix A minus lambda I. So you do have your square matrix, then you subtract the product of lambda by the identity matrix from it. You find that. That's called a characteristic polynomial. It's actually a function in lambda. And if you set this to 0, then you get an equation which you can solve. And so the values of lambda that come out are called the eigenvalues. So I don't remember. I should have checked. But anyway, if I explain to you how to find the corresponding eigenvectors of the eigenvalues. So I mean, if I explain to you, good for you. If I didn't explain to you, well, still good for you because I explained to you now. And we look at an example. And actually, specifically, we look at the card that I gave you, which was comprehensive, which I'll intend to review in the next few minutes. So, um, to get the eigenvectors, once you have the eigenvalues, all you need to do is solve. You will have what you call the eigenspaces, An eigenspace will be corresponding to the eigenvalues, lambda. So the eigenspace of lambda would be, it will be a set of vectors whose, actually this matrix, A minus lambda I is a matrix. That's why you're finding this determinant. So the null space of this matrix, you know what a null space is? Null space means the solution to the homogeneous system of linear equations whose coefficient matrix is our matrix A minus lambda I. So that solution will be the eigenspace. And so we pick one vector from there, and that will be the representative vector for our eigenvalue lambda. Lambda can be 1, 2, 3, a half, whatever it is. So really, how you solve that is just to say, you just put here A minus lambda I, and then you put 0. You know why? Because this is how you solve a system of linear equations. Hopefully making use of the Gaussian elimination or Gauss-Jordan elimination method, all right? So this is now a system of linear equations. This is the augmented form of the system of linear equations. So what do you need to do? Well, you need to apply the row operations to reduce this matrix into row echelon form. Then you read the solution, the corresponding values, the pivot, the free variables, and get your solution, all right? So that is a good preamble for my vision for the cat, which is more like, yeah, I might be doing new stuff as I do old stuff at the same time. All right. So now let me see what this screen of mine will allow me. So where are we going next? Here it is. So this was the card that you were given to do. Is it? Yes, it is. Continuous assessment. All right. which was due on 30th of June, I believe. Now, if you have not submitted by the time you look at this, then you know that you are time bad, okay? Ideally, it was supposed to be, when are we? Today's Friday. Yeah, this Monday was the deadline I extended, okay? Monday was Saba Saba, I believe. Was it? Wait, when is today? Now I don't even know. I'm confused. But yeah, I think it was 7. Anyway, that's why I'm giving the solutions now. So, classify the following statements as true or false. Ideally, it should have been classify the following statements as true or false. All right. So, 1, if the determinant of A equals 1, then A equals I. I is the identity matrix. So, is that true? Well, one of the things we know is that the determinant of a matrix is a diagonal matrix whose entries, basically in the main diagonal, are ones, 1, 0, 0, 1. That's I2. Let me just write here for you again, because mathematics is visual. So I, for 2, I can say I2 is 1, 0, 0, 1. What's the determinant of this matrix? Is 1 times 1, which is 1, minus 0 is 1. So the determinant of this matrix is 1. Well, I can give you another matrix. I can call it whatever it is, but I can just say something like, I don't know, 1. I can put this as 1. I can put this as 0. I can put this as 2. And then I ask you, what's the determinant of this matrix? 1 times 1 minus 0. This matrix has determinant 1, and it is not equal to the identity matrix. So this statement is false. Finished? Yes. Next, the set S equals 1, comma y to z, where y plus z is 0, is a vector subspace of R3. So a nice way of thinking of this is just if you pick any values of y and z in the real number set, and then you arrange them this way, the first one will always be 1, then y and z will be whatever y you pick, and then twice whatever you pick as z, right? So we claim this is, well, the question is this a vector subspace? Well, for a vector subspace, vector subspace and a space for that matter, because a vector space is a subspace of itself, must have the 0 vector, all right? In this case, our 0 vector will have when y is 0 and when z is 0, right? This would be our 0 vector, which must be in any subspace of R3. But now this one is not here because the first guy must be 1. So this is false again. Now, number 3 is a little bit tricky. I ask you guys to read about onto and one-to-one linear transformations, but I just tell you that, in this case, you are asked to show or check whether this linear transformation is onto. Now, what does that mean? Well, onto, you can just translate the same language you had for functions. When do you say a function is on one-to-one? Actually, we're looking at one-to-one. When you map, okay? If whatever you send, if I pick XYZ, I send it here, and I pick something different, I send it here. Whatever I'm getting, those two, if they're equal, then the origin is also equal. The original one. When I talk about original, think of a mirror. When you look at yourself, you see the image of yourself. So you yourself is the original. What you're seeing is now the product of the image, all right? So in this particular case, I just make one statement that this is supposed to be false. And the reason for that is because X and Y are okay. What is not okay is Z, because Z can be anything. Meaning that I can have X and Y to be anything which will give me something similar. Because we have no restriction for X and Y, or for Z. Now, I had solutions. Let me see whether I need to give you the solutions for all this. Let's just go back here. Probably this will be helpful to you. So here I have some solutions, which I hope they will be helpful. Oh gosh, what is this now? This went to, well, I don't seem to have a solution for this. My slides are a little bit, well, this is not what I want to talk about. So allow me to go back to our our questions. I think I'll answer it in one way or another. Oh gosh, how do I do this now? These screens. Okay, there it is. Okay, so I have slides, but for this particular part, I didn't write down anything because I figured I just explain to you, and if I need to write, I just write on the screen, which is exactly what I'm going to do. So to check whether a linear transformation is on one-to-one, what do you need to do? Well, you suppose, I mean, you can say maybe you once you apply, I have two vectors. Maybe I can call one vector u, all right, which will have an x, y, z, and another vector v, which will have something, an x, y, and z, all right? And then I need to show that T of u, suppose T of u, so you assume T of u equals T of v. You suppose this is true. Here, I could just tell you, maybe you can just say, I don't know how you want to say it. You can say this is ux, uy, uz. All right? If you pick a vector, which is ux, uy, uz, and then you pick another vector, v, now your v is vx, vy, and vz. Okay? So you have these two vectors. Then you apply the linear transformation you're given. Now remember, our u must come from R3. That's why you have x, y, z. Our v must also come from R3. And then now whatever you send it to is R2. How does that occur? The first two guys you add and the first two guys you subtract. Take the difference. So T of u, and then you assume, suppose T of u equals T of v. What do you mean by that? Well, this means that it means that here you'll have u of x. The first two guys you add, so it says ux plus uy. Comma, ux minus uy. Ux minus uy. So this is this. And this is, I mean, so first you assumed, okay, let me just write it here. Suppose this equals this. The next step is, what does T of u do? Well, under this map. Well, it just adds the first two, takes the difference. So you get that. And this should be equal to, because you already assumed, T of v, which will be something similar, will be vx plus vy, comma, vx minus vy. And so we are almost done because now what does this mean? If these two guys are equal, it means that you see these are two vectors you have. The first guy must be equal to the second guy. So it means ux plus uy equals, now we can write it somewhere here. Ux plus uy must be equal to vx plus vy. Because these are two vectors, and the way they are arranged means that the first guy must be equal to the first guy. The first guy is an x corresponding guy. Remember, these are two guys, so they belong to R2. I mean, and then the second guys are equal. So ux minus uy equals vx plus vy. And now we conclude, we're almost finishing, because now if you have these two sets of equations, so if you add these two equations, what happens? You can see ux plus uy. If you add the left-hand side, you have ux minus uy. So this plus this, the uy disappears, you end up with ux equals, look at the left-hand side. Right-hand side is, well, did I do anything wrong? Yes, I did. This is supposed to be minus. Let's just correct it so that I don't get you lost or mistaken in any way, yeah? So this one here is supposed to be, remember, this is ux minus uy must be equal to Vx minus Vy. Okay, so left-hand side we added, this disappears. You have Ux equals Vx plus Vy plus Vx plus minus Vy. So you end up with Vx. So Vx equals Ux equals Vx, which is good. And now if this is the case, then that means if you substitute this one here, you have Ux, which is Vx, right? So these two guys go away. So you end up with Uy equals Vy. If you don't see it, again, look at this. If I substitute Ux equals Vx here, this is Ux plus Uy equals the same Ux plus Vy. So Ux goes away, you end up with Uy equals Uy. Uy equals Vy. Now, for this to be one-to-one, it means that Ux must be equal to Uvx, Uy must be equal to Vy, and Uz must be equal to Vz. But that doesn't come out. That Uz is not forced to be Vz from our working. So we cannot conclude that this is one-to-one. Hence, this is false. So actually, the answer for all these guys was false, 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 false. That's how you would work it out. Right, number two says, suppose A is a 5 by 5 matrix, a matrix of order 5, and the determinant of A is 5. So what is the determinant of 5A? Well, all you need to remember is the effect of multiplying, the effect of the determinant of multiplying any row or any column by a non-zero scalar. And this is more like the effect of the determinant on determinant on any of the row operations. So in this case, you see, since 5 is multiplied, the whole matrix is multiplied by 5, it means that each row, if I have a matrix, I don't know, you want the matrix to be 1, 1, 2, minus 1. When you multiply by 5, it means that this matrix becomes 5, 5, 10, minus 5. Means each row is actually scaled by 5. So the determinant is also scaled by the multiple for the number of rows that you have. So here we have how many? So the determinant of 5A will be the determinant of A, but now this one will be how many copies of that? 5. Why 5? Because there are 5 rows or 5 columns, you want to say. If you're thinking of it in terms of rows or columns, is that each of the rows or each of the columns is to multiply by 5. Look at what happens. What's the determinant of this guy here? Is 1 times minus 1 is minus 1, minus 2 is minus 3. Now, if you scale by 5, it becomes minus 15. Is that correct? Have we done the right thing? And why is that? Wait, is that true? Have I said the correct thing? No. No. So the determinant of this matrix here, this one here, is minus 3. What's the determinant of this matrix? We expect it to be what? We expect it to be how we are scaling. So this will be multiplied by 5, multiplied by 5. So it's supposed to be minus 3. Wait, let me see whether I'm saying the right thing. Probably I'm not saying the correct thing. So the matrix here, let's conclude. So the new matrix we get is 5, 5, 10, minus 5. The determinant of this guy is minus 25, minus 50, so it's minus 75. So how does minus 75 come about? From arguing from here, this determinant is minus 3, right? So the determinant, so you do square. So this times 5 gives us 5 times 5, which is 25. Does that make sense? I hope so. All right. So when you multiply by 5, one of the rows, the determinant is multiplied by 5. So it is the determinant actually, yeah. So here I should just say, what's the determinant here? So it will be the determinant of A which is 5, you multiply by how many number of rows and columns do you have? There are 5, and then you raise to power 5. The determinant here is minus 3 times how many rows and columns do you have? 1, 2. There are 2, but then you multiply by, no, it's the 5, the constant, the number is 5 you are scaling with squared. So here the number is, the determinant is 5 times 5 power 5. That's what the number should be. Okay, that's more like a manual way of doing it. All right, now the last, second last thing, this I've taken too long in this one. Suppose so that T, this map defined by this is bijective, it's a bijective linear transformation and determine its inverse. Because it's 10 marks, so it's a lot of marks because there's a bit of work to be done, like this, what we did here. So the first thing you need to do is you show that this is, actually, how will you do this? There's a theorem that I mentioned to you earlier on from the book that I gave you. And what does it say? It says, you see, every matrix represents some linear transformation. So any linear transformation you have has a matrix that represents it, or is represented by it, okay? So in this case, all you do, the first thing is you pick the matrix. To solve these things at the same time is 1. You pick the matrix of this linear transformation. So the matrix of the linear transformation, allow me to call it T of A, or TA. I don't know why T of A. T is a linear transformation with respect to the matrix. So I call it, now, what is the matrix of linear transformation, of this linear transformation? Well, for the first guy, the coefficients of X and Y are 1, 1, and then Z is 0. The second one is the coefficients of X is 0 here, so you have 0. Coefficient for Y is 1. Coefficient for Z is 1. Then the last one, the coefficient for X is 1. Coefficient for Y is 0. Coefficient for Z is 1. So this matrix is the representation. This linear transformation is represented by this matrix. That's what I want to say. Because if you multiply X, Y, Z by this matrix, you get X plus Y, Y plus Z, and X plus Z. So now, if this matrix is, well, there are several things about the theorem I was going to tell you. One is that if you reduce this, if the determinant of this matrix is not 0, then this matrix is invertible. That's one thing you can say. 1. 2, you can say that then the linear transformation that represents, this is represented by this matrix, is actually 1-to-1 and onto. It's bijective. This bijectivity means it is 1-to-1 and onto. And this is guaranteed by the fact that the determinant of this matrix is non-zero. That means the inverse of this matrix does exist. That means this linear transformation that is represented by this matrix is bijective, is 1-to-1 and onto. And the inverse exists, so we can find it. So, and finding this, I don't think is a very complicated process. Let me see whether, I think we did this. If you have not done it, you did the work, and so for some of you have checked, it's not too complicated. What do you do? Well, the first thing you do is you need to find, to find the inverse of this matrix, you can do it in 2 ways. One is you can apply the cofactors. That means you need to work out the cofactor of each of these entries. So you get the cofactor matrix. I can call it I don't know, C, or how do I call it now? C, for cofactor matrix of this matrix. Now, you remember the cofactors? I don't want to work that out, but it's not a very complicated way of getting cofactors. Cofactors means that, the cofactor of 1 will just be the determinant of this matrix multiplied by 1. The cofactor of this 1 will be minus 1 times the determinant of the matrix you get by deleting this row and this column, or this column and this row, all right? And so on. That's how you're getting cofactors. So you find the inverse of this matrix. It's not too complicated. using the cofactor method. That's one way of doing it. The other way of doing it is to use the row reduction. So let me, probably this is the one I can attempt. Now I just say attempt because I don't know whether I have time. I do have time, so there's no problem. So let's do this. Let's first erase this so we can have space here. So what you do, I think I've already mentioned to you, you write it in this special augmented form. You start with your matrix A. Okay, allow me to use A for the sake of making my life easy. And then you apply the row operations to this matrix so that you exchange the A with the I. So you'll have I here, and whatever will end up on this side turns out to be I inverse. That's basically what you do, all right? And so, I mean, I say that we have time, so let's see whether we can do this. So we write it down. We just have 1, 0, no, oops, sorry. So what do we have? We have 1, 0, 1. Then we have 1, 1, 0. Then we have 0. Then we have 1, 1. So that's our matrix. Then now you write adjusted to it the identity, which is a 3 by 3, which is 1, 0, 0, 0, 1, 0, then 0, 0, 1. And so now this is the AI. Now you apply the row operations to this. So let's do that, okay? So all you need to do is, you remember, I mean, row operation or row echelon. Yes, you apply row operations to go to row echelon form. So how you do that is just to make it the non-zero here, and then you step on zeros. So the first one, we can fix this first row. We just have 1, 1, 0, next to 1, 0, 0. Next, this one can stay as it is because it's already a 0. So 1 is already stepping on a 0. So that's already good. So we can be happy about that. 0, 1, 0. So row 1 fix, row 2 fix. Row 3 will be row 3 minus row 1 or row 1 minus row 3. I don't know, whatever you like. I can just pick it as it is. So 1 minus 1 is 0. And then I have 1 minus 0 is 1. And then I have 0 minus 1 is minus 1. And then we have 1 minus 0, 1. 0 minus 0, 0. And 0 minus 1, minus 1. And so the first column is a non-zero stepping on zeros. So now we have 0 here. Now we need to make a 0 here, like that. So now we play around with row 3 again. But now we want to, well, yeah, let's go that way. So what do we have? We still have 1, 1, 0. Then 1, 0, 0. This one we say we keep it as it is. So it's 0, 1, 1. And then this is 0. This is 1. This is 0. Then now what do we want? We want a 0 here. So we just subtract. So 0 minus 0 is 0. 1 minus 1, 0. 1 minus minus 1 is 2. And then 0 minus 1, minus 1. And then 1 minus 0, 1. And then 0 minus minus 1 is 1. So are we almost getting somewhere? Yes, because now this what we have is already in row echelon, but we needed to make it like this. We need to make this first part 1, 0, 0, 0, 1, 0, 0, 0, 1. You can see we are almost there because this guy, if you divide by 2, we are there. So that's good. So this will just divide by 2. I can just say this one, divide by 2. So we'll be there. You can see where there is that the 3 by 3 first part should have 0, 0, 1. Then this one, you just need to subtract that one here. So once we get the 0, 0, 1, if we subtract the 0, 0, 1, I mean the 0, 1, 1, 0, 0, 1 from the other one, we'll get somewhere where we're going. So it's looking good. And then the first one, we can already get a 0 here by subtracting what we'll get at the end there. So let's do that, okay? Allow me to scroll a little bit. Do I have space or this thing has refused? Okay, well, we just use the space we have nicely so that life is good. All right, so next, I'll go this way so that I use the space well. So the first one, first row, I just keep it as it is. So let's just write here. This one we divide by 2, we just get 0. We get 0. We get 1. And then you have minus a half. And then what else? We have a half. Then we have a half. All right. So that's good because the third row, now we can subtract this guy from here so that we get the second row 0 to be 0 minus 0 is 0. 1 minus 0 is 1. Then 1 minus 1 is 0. You see, this is already looking like an identity matrix. It's taking that shape, so we're almost there. Next, we have 0 minus a half is a half. Next is 1 minus a half is a half. Oops, what has happened to my, and it's running away very far. All right, and then we have 0 minus, no, where are we? Here. So this is 0 minus a half, minus a half is a half. 1 minus a half is a half, and 0 minus a half is minus a half. And ladies and gentlemen, you can see we're almost home. In fact, we are home. Because what do we need now? We need this guy. We need a 0 here. So just this guy, we subtract this one. So we have 1 minus 0, 1. 1 minus 1, 0. 0 minus 0, 0. And you can see this first part is an identity. So let's complete this one so we get our inverse. That was not very painful, was it? No. All right, so we have 1 minus, what are we subtracting, by the way, so I make sure I don't get confused. So we are subtracting these ones, this, so 0, 1 minus 0, 0, 1 minus 1, 0, 0 minus 0, 0. Then you have 1 minus a half is a half. Then you have 0 minus a half is minus a half. Then you have 0. Where were we? 0 minus a half is a half. And so now what have we ended up with? We started with this thing, this one, this is the AI, and then we have ended up with IA, the inverse. So the inverse of this matrix, now this time around I will call it TA inverse, is, I will pull out the half. You can see the half is, clearly the determinant is a half. Should I say clearly? Well, I mean, if you pull out a half, you get 1 minus 1, 1. Then you get a 1, 1, minus 1. And then you get minus 1, 1, 1. So now this is the inverse of this matrix. But what is this matrix? This matrix is the representation of the linear transformation that we had. So now we needed, the question was asking you, show that this map, this linear transformation is bijective, linear transformation, and determine its inverse. So now you're almost there, you're not finished. What you need to find now is, you need to write down T inverse, all right, takes, like this one, X, Y, and Z from R3 to R3. But what does it do exactly? It turns out that what it will do exactly, it will be a half. Then you multiply everything by. So here I just put X, Y, Z. Allow me to do that. This is A. I put X, Y, Z here. If I do that, me multiplying this matrix by this XYZ tells me what I'm doing, the inverse transformation. So this will be X minus, so it will be X minus Y plus Z. And that is the first guy. Next, you multiply this by that, XYZ, you get X plus Y minus Z. And lastly, you multiply by the third row, you get minus X plus Y plus Z. So now the fact that, let's just finish writing it down. So this, ladies and gentlemen, is T inverse, takes R3 to R3, it takes an XYZ to this thing. So basically what we are saying is that this map, this linear transformation, is a bijective linear transformation if the determinant is non-zero, or if you can find a matrix, you can find the inverse of the matrix that represents the linear transformation. We have found that matrix. And so we can conclude this linear transformation is bijective, it's one-to-one and on-to, and we can actually write down the inverse, and this is it. So all that work we've done, they look very complicated, but it's actually a lot of very interesting stuff. So I believe it was fun. So now I want us to go to the next thing. What was the next thing? Question 4, 5, 6, 7. These are not very complicated. I don't want to make this video too long. So prove that the determinant of A inverse equals one of the determinant of A. This I will say that if you check in your book, this explained to you very easy, because determinant of A, you bring in the issue of determinant and product of determinants. So if you write A times A inverse, the determinant is the determinant of A times the determinant of A inverse. But the determinant of A times A inverse is 1, because it's the identity. So that you can figure out, that's not too complicated. Number 5, prove that AB raised to power minus 1, basically the inverse of A times B, is same as the inverse of B times the inverse of A. This again, the same proof similar to this one. You just take this guy, you just take AB times B inverse A inverse. And then you open up the brackets and play around it. It will give you the identity, so you are done, okay? Then use these matrices to illustrate the result. It's not very complicated. Now, number 6 and 7, this is now where the part I had some slides to show you. So for number 6, describe the conic given by this equation. So here I have something nice for you. Let me see whether I do have something nice for you. Yes, I do. So let's erase this so you can see it. Now, how much time do we have? Maybe 5-10 minutes maximum. All right, so I just erase this very quickly. My eraser is not the best, but okay, fine. So, what is it that we are supposed to look at? Yeah, so we are given a quadratic form actually. For x squared minus 6xy plus 4y squared minus 8 is 0. So this we can take the 8 to the right-hand side. We have 4x squared plus minus 6xy plus 4y squared equals 8. This can be expressed as, we write this in matrix form, which is a quadratic form. We have a variable matrix times its transpose, and in the middle you have this matrix, which is symmetric. Symmetric means that the matrix and the transpose are the same. 4 minus 3 minus 3, 4. If you transpose, it means that you exchange this row becomes a column, and this column becomes a row, and so on like that, okay? So the characteristic, so here now we look for the eigenvalues, and then consequently the eigenvectors. So how do we go about that? Well, the characteristic polynomial, P of lambda is A minus lambda I. So it's just, usually lambda I is just the diagonal, which has lambda 0, 0, lambda. So it's 4 minus lambda minus 3, minus 3, 4 minus lambda. Then now this you equate to 0. You have this polynomial, 4 minus lambda times 4 minus lambda minus 3 times minus 3. This turns out to be this equation, which is lambda squared minus 8 lambda plus 7 equals 0. And you can see this is asking you to factorize whose factors of 7? They give you a sum of -8. Those numbers are just -7 and -1. -7 times -1 is 7, and -7 plus -1 is -8. So this factorizes into lambda -1 times lambda -7. The values of lambda are 1 and 7, and those are the eigenvalues. We are finished. The diagonal matrix corresponding to our matrix A is the matrix of the eigenvalues, which is 1, 0, 0, 7. Next, the eigenvectors. How do you go about them? Well, not very complicated. The null space of A minus lambda I. Now you have the lambda values, so you just go here and substitute the value of lambda. What's lambda? Lambda in one case, it is, when lambda is 1, you'll be talking about 4 minus 1, which is 3, minus 3, minus 3, 3, 0, 0. You're solving this system of linear equations. So if you apply what we've just done, the row operations to move this guy to row echelon, you can see this is a multiple of this. So you add the two guys, it gives you this. And now this tells you if you have the two variables, x and y, the y variable is, what do you call it? This is pivot, x is pivot, y is free. And so this equation gives you x equals y. So the solution is xy, y value is 1, then x will be 1. So the vector corresponding to lambda 1 is 1, 1. The eigenspace for 7, now you replace 7 here. You have 4 minus 7 gives you -3, -3, -3, 4 minus 7, which is -3, 0, 0. This you apply the row operations again, you get 1, 1, 0, 0, 0, 0. I mean, you just add the two guys, or rather subtract. And so now this again gives you our x is pivot, our y is free. So x equals to minus y. So when y is 1, x is -1. So this is the eigenvector corresponding to 7. So A is diagonalizable. That means you can express A as MD, M inverse, where D is this and M is D. Now, the next thing I said here, let me just erase this very quickly, was that we can now take a step further and not only just say A can be diagonalized expressed in this form, but we can notice that these two vectors, if you take the dot product of 1, 1 and -1, 1, you get 0. So these two are said to be orthogonal vectors. You know, they are like perpendicular. And then the length of these two vectors, the length is just x squared plus y squared square root. So it's 1 squared, 1, plus 1 squared, 1, square root of 2. So the length of these two vectors is √2. So if you want to make them unit length, you divide by 2. So you have 1 over √2, this vector, 1 over √2, the next vector. Okay. Now I hope this will agree with me to give me the other slide. So life is easy. All right, so there it is. So now the next step was from M, which is 1, 1, -1, 1. We can say now this is unit. Can get a new matrix, which is P, which is 1 over √2, 1, 1, -1, 1. And so now A can be written as P diagonal matrix P inverse. So the original one, which we had, was VT, variable transpose, times A times V. We can transform it now. We replace the A by this. We end up with P transpose times V transpose, diagonal matrix PTV. Now, what does that really give us? Well, this tells us that we modify from the XY plane to a new variable. I'm calling X dash Y dash variable. So this is now telling us that this is how you modify. The old variable is XY. The new variable, let's just erase this. Hopefully we have time, maybe less than a minute or two. So we end up with this. So the original thing now becomes this. The diagonal matrix, 1, 0, 0, 7 times the new variables. So it becomes x dash squared plus 7y dash squared equals 8. You divide by 8, you end up with x dash squared over 8 plus 7 y dash squared over 8, or x dash squared over 8 plus y dash squared over 8 over 7 equals 1. Now this is like a circle, only that these two are not equal. So it's a circle that is compressed. We call that, you know, pressed or deformed. An ellipse. So how do you get the transformation? If we get a vector v 1, 0, this is modified by this matrix of ours. So you multiply, to get v dash, you multiply p transpose times v. So 0, 1 moves to 1 over √2, 1, 1. So if this is 0, 1, it moves somewhere here. So the original horizontal axis is this, the new one will be this one. And to get the other one, we just say the perpendicular of that one. So if this is x, y will be this one because it's perpendicular to it. So if this is x dash, the y dash will be this one. And so now if you measure a small distance of 8, this is more or less 8. From 0 to here is about 8. And then this one is 8/7, which is about 1. So this is measure 1. Then you just sketch like that. And guess what, ladies and gentlemen? Finished. Actually, that's it. I mean, anything else I was going to say is now if you go higher, but I don't want to go higher. So let me just end there. So thank you very much. I think we can stop there.